Respected judges, Assalamu alaikum. We are Team MPCs participating in the high school level of Teknofest 2026 Technologies for Humanity competition. Today, we are honored to present our project Alga-Pave.
Thank you, Ryan. Alga-Pave is a bioluminescent microalgae urban surfacing system. Our initiative re-engineers modern city pavements, transforming passive surfaces into active biological ecosystems.
My name is Mohammad Rayan Zia, and I am joined by my teammate Mohammad Ursal Jishan, and we will be your hosts for today.
Okay, so traditional concrete and asphalt act as thermal batteries, storing solar radiation and raising ambient temperatures, while also trapping pedestrian level toxic emissions. The prior project Alga-Pave directly counters this infrastructure crisis. Our solution utilizes high-strength translucent polycarbonate pavement tiles, embedding live microalgae cultures of Chlorella vulgaris and Spirulina planthisis. This is paired with a subsurface evaporative cooling grid and a secondary bioluminescent light circuit powered by a proprietary specific furnace. The expected impact includes an active surface temperature reduction of up to 5 degrees Celsius, direct street level carbon reduction, and grid-free pedestrian path illumination. This aligns directly with the category guidelines.
Our primary purpose addresses critical public health disparities by mitigating the urban heat island effect and street level carbon saturation. This is a matter of environmental justice. A lack of urban green spaces disproportionately impacts vulnerable demographics in dense municipal centers.
By treating clean air and cooler microclimates as the baseline human rights rather than exclusive amenities, we alleviate energy poverty through self-sustaining grid-free street illumination. Furthermore, we implement a cradle-to-cradle cycle where harvested biomass is processed into organic biofertilizer and local biofuel, returning valuable nutrients to the green community spaces. So now to understand the problem, we must first analyze the thermal inertia flaw. Conventional paving systems dominate up to 40% of city footprints, absorbing crushing solar radiation. This creates a severe pedestrian exposure zone where the street surfaces spike from 50 degrees Celsius to 70 degrees Celsius, exactly where citizens walk and breathe every single day. Every single 1 degree Celsius spike in urban nighttime temperatures causes a documented 2.2% increase in mortality among vulnerable demographics, as shown in the graph. Compounding this street layouts acts as a carbon boundary layer, trapping heavy vehicle CO2 concentrations between 1,000 and 2,000 ppm, massively exceeding the 421 ppm global baseline.
Existing mitigation approaches cannot scale effectively. Urban tree constraints like limited soil depth, complex subterranean utility networks, and structural load rules render large-scale city planting impossible.
Simultaneously, cool pavement coatings are passive options, yielding a minor 1 degree Celsius to 3 degrees Celsius mechanical delta. They fail to capture CO2, provide zero illumination, and wear away rapidly. Lastly, green roofs suffered from urban isolation. They insulate buildings but leave the pedestrian and the streets unmitigated. Our proposed solution breaks this vacuum through a highly modular infrastructure where we introduce interchangeable pedestrian bioreactor tiles that drop directly into pre-existing municipal grids without replacing or requiring major trenching, long closures, or structural overhauls. The frame utilizes an advanced polymer shell made up of translucent, heavy-load polycarbonate panels optimized for maximum light transmission and rugged non-slip safety. Inside one are biological air scrubbers housing high-density Cholera vulgaris and Spirulina planthisis colonies optimized to handle extreme heat temperatures up to 40 degrees Celsius, pulling in precisely 1.82 grams of atmospheric CO2 for every single gram of cultivated biomass.
Our closed-loop bioengineering process flow diagram features a dual-phase multi-layered metabolic cycle. The first layer is a hydro-vapor cooling interface, a subphase water channel driving moisture through microperforated structural sinks.
And by utilizing water's high latent heat of evaporation, which is about 220 to 60 kilojoules per kg, our thermodynamic regulation actively lowers localized ground temperatures by up to 5 degrees Celsius. For the night phase, our dual-phase metabolic switch opens a secondary isolated biological chamber housing proprietary furnace, which generates a soft ambient blue-green light at 475 nanometers peak wavelength with absolutely zero electricity.
We validate this architecture through real-world prototyping to prevent cell mortality and maintain monitor home stateness, we embedded sensors tightly regulate the internal fluid pH within an optimum range of 6.5 and 8.5.
Our thermal suppression data is outstanding. With peak simulated solar conditions of 950 watts per meter square, our testing recorded a maximum localized surface temperature reduction of 5.2 degrees Celsius. Furthermore, our photosynthetic gas exchange confirms high velocity carbon conversion with zero gas lock inside the polycarbonate shell. Continuing with the operational prototype testing, we tracked our bioluminescence resistance curve. Our engineered proprietary photoformist strain achieved sustained light emissions at 475 nanometers, providing glare-free pedestrian flow illumination across the critical 6-hour night cycle. Our automated neutron loop performed flawlessly as well. Hardware pathways showed automated solenoid valves activating instantly upon neutron depletion. Furthermore, our pedal extraction trials proved that dense biomass could be successfully harvested via flush valves without disturbing the physical tile layer.
The commercialization potential of Alga-Pave completely redefines urban asset management. We transform standard urban pavement from a compounding maintenance liability into ongoing municipal revenue generating assets.
Our integrated biomass harvesting infrastructure uses periodic automated flush cycles to route algae biomass out of local tile networks into centralized hubs. This material is processed directly into organic biofertilizer for municipal parks or converted into liquid biofuels to offset municipal transit power costs.
From a sustainability standpoint, Alga-Pave completely avoids the toxic supply chain, rare earth mining, mineral resource constraints associated with standard solar pavements. Using purely biological pathways, they leave zero electronic waste footprint at the end of their life cycle.
Our pilot formatting is designed for rapid adoption. Deployment can launch using minor 50 to 100 square meter urban testing footprints, expanding seamlessly as performance metrics scale up. This modular scalability fosters strong partnerships between municipal councils, green builders, and biotechnology suppliers. So our target market deployment is sharply defined across four key high-impact sectors. Firstly, there's urban planners and architects seeking sustainable public infrastructure layouts. Secondly, city councils and municipal governments facing severe urban heat crisis. Third, pedestrian corridors and public plazas where human density is the highest. And last but not the least, are transit forecourts and stations where idling vehicles emissions create hazardous localized carbon bombs.
The collective benefit of Alga-Pave revolutionized modern urban living across three clear pillars: human health, lowering street temperatures by 5 degrees Celsius reduces respiratory stress and prevents heat strokes among vulnerable citizens. Under environmental sustainability, our tiles scrub heavy vehicular carbon dioxide right at the point of origin. And under daily urban life, we transform dark pedestrian corridors into softly lit, pleasant, and highly attractive, breathable spaces.
So our engineering roadmap is set across a disciplined 10-week timeline divided into 5 work packages. Work package 1 handled the biological research and strain selection from weeks 1 to 2. Work package 2 advanced style engineering, stress testing, and gasket layouts from week 3 to 5. Work package 3 completed the fluid modeling from week 5 to 7. Work package 4 is just finalized the hardware control sensor loop coding and board assembly in weeks 7 to 9. And culminating in work package 5 will be the total system integration and structural scaling across the next few weeks. So our strategic SWOT analysis highlights our operational readiness. Our strengths lie in our dual-phase design, solving urban heat, and lighting with zero rare earth mineral reliance. Our weaknesses acknowledge higher initial fabrication costs compared to raw concrete, but that is just given, and a drop in biological efficiency in high humidity zones. Our opportunities are immense, integrating directly into smart city networks and international carbon credit frameworks. Finally, some threats are limited exposure to prolonged sub-zero freezes, which risk fluid crystallization, a factor which we do actually mitigate through subsurface thermal regulations. So now, judges, we can no longer afford to build our expanding cities out of dead, oppressive materials. It is time for our infrastructure to work just as nature does to preserve human life. Team NPCs is proud to lead this change, as our slogan states.
Alga-Pave, paving the path for living infrastructure, building the breathable cities of tomorrow.
Thank you for your time. Tashakkur Lair ve Allah Hafiz.